Um, Welcome everybody. Welcome to the next rebase session at the 2020 Splash. It's my great pleasure to introduce Matt Bauman, who is a senior research scientist at Julia Computing. He works out of Chicago. He's got a long history of working on usable high performance computing. And I look forward to hearing the talk on differentiable programming in Julia. Thank you, Matt.
Great. Thank you so much, Raz. Thank you everyone for being here. I am really excited to talk about the kinds of things that we're doing in Julia, particularly as it relates to differentiable programming and how differentiable programming, we abbreviate it with that partial P symbol, how this is enabling a whole new science in Julia, a whole new field. And I want to talk about specifically how this looks, what kinds of things, we're doing, what this enables. So we'll start off with a very, very brief review of derivatives for those of you like me who has been a long time since you've been inside a calculus classroom. Just a very brief overview of what they are, how we work with them. But then I want to do a deep dive into what's commonly called the inverse problem. And we'll see how that plays out, particularly with respect to throwing things with a trebuchet. So it's kind of a fun, interactive example where we can do lots of different ways of derivatives and really see three key ways in which derivatives can help us understand systems and model them better. And then lastly, I'll go through some of the real science, right? We're not actually using trebuchets to do real science, but it's a great story and a great way of understanding it at a very fundamental level. So that way, when you see real science being done that's far more complicated, you can understand and you have a grounding in what's happening. So let's kick this session off with derivatives, right? In a high school calculus, your college calculus classroom, you probably did some sort of derivative of an expression like this, right? We can define a simple polynomial in Julia just as a one-liner, 4x cubed minus 3x squared plus 2x minus 5. We can plot that thing really easily. And if we want to take a derivative of this plot at a particular point, say at 2.5, along the x-axis, well, it's as easy as drawing a tangent line, right? You just draw a line tangent to the curve, and that's your derivative, your rate of change with respect to x at that given point. And in calculus, we learned how to do this, right? We learned the chain rule and all the different ways of doing it. You pull the 3 down from the exponent, multiply it by the 4. That gives you a 12, and x squared minus 6x plus 2. This is the general form solution for this derivative, right? And I can define a second formula, a second function in Julia that will give me the derivative at a particular point. And this is just me using my knowledge of calculus and saying, hey, let's re-implement this function f as its derivative and create a new definition, right? Manually do this using my knowledge of calculus, teach the computer how to do this. And then I can ask, what's the derivative at 2.5? And sure enough, it'll tell me it's some relatively large positive number. Now, why might I want to know this? Well, a perfect example is in gradient descent, the algorithm that underpins all of machine learning. You want to improve some system. So you'll say plot the error along the y-axis, and you want to improve that error, decrease that error as much as possible. And so the derivative tells you simply which way to move and potentially how quickly to move in that direction, right? And so this is a very concrete task that's underpinning whole swatches of science these days. Now, this is a really simple example, right? It's an example in which it's closed form and in which there's nothing dynamic going on. It's completely continuous. Things don't change as you change the input, right? The system is the same. But once we start talking about the derivative of a general program, things get more complicated, and they get more complicated quickly, right? Because we're in a general purpose programming language that could have a crazy function, right? So here's another function definition where if x is negative, well, we'll do some IO, print out a prompt for the user, ask them to enter a function name, and then we'll read that in Julia, dynamically look up what function that is, and evaluate it at the x that's given. Otherwise, let's do that polynomial that we showed in the first example. So if positive numbers, I can evaluate that polynomial. That's just great. Negative numbers, I execute this, and Julia will prompt me, right? It'll ask, what function name do I want to use? I type in sine here and evaluate it, and sure enough, sine of negative pi over 6 is negative 1/2. I can do the same thing at a different point and enter a different function name, right? And say, let's do a cube root of negative 27. That'll give me negative 3. And this is kind of a crazy example, right? That we're dynamically typing in code to be evaluated and looked up and understood. So if we truly want a differentiable programming language, how in the world would we do this, right? You can't just go out and write a closed form solution for this. We actually have to look and see what the user wrote, look and see which branch we took. There's a discontinuity here, right? And that happens all the time in real world examples. In calculus classes, we've been taught that discontinuities are bad for some reason or scary. No, they're fine. You just go into that branch and take the derivative of it. But we need to take the derivative of some crazy things here, including how you look up things and execute them and everything. So is this something that we could potentially do? And sure enough, Julia, as a fully differentiable programming language, has package support for a special syntax where you apply some postfix operator to a function. In this case, it's that apostrophe, a very mathy looking sort of thing. And that will ask for the gradient with respect to the argument at the point that I passed in. So of course, if I ask for the gradient with respect to the argument at the point 2, it'll give me 38. And again, that's just doing the exact same calculation that I did before, very similarly to what I did earlier. But now let's give it a negative number, right? I can give it a negative pi over 6. Again, type in sine here, hit enter, and I get back root 3 over 2. Right? That's the derivative of cosine here. We actually have a programming language that can do this sort of crazy thing that it's it's not continuous, and yet we can do this and we can keep doing it. Right? It's not hard coding that sine in. I evaluated a different point and do that cube root, and sure enough, that's the derivative of a cube root function at negative 27. So if you're interested in how exactly we do this, I encourage you to check out Kano Fisher's talk from Monday. He gave a talk about the kind of infrastructure that we've been developing in Julia that supports this and underpins this. But I'm just going to take this for granted, right? We have this cool capability that Julia code is fully differentiable and run with it. So that's my introduction to derivatives. Now let's talk about the throwing things, right? How does this relate to aiming a trebuchet? So let's say I have a trebuchet. I have access to a medieval siege weapon in my backyard. I have a 220 kilogram counterweight. I have a projectile, and I want to hit a target 100 meters away. How do I do this, right? How do I just set up my trebuchet so I can hit that target? I can really just change two things. I can change the weight of the counterweight that's going to crank that arm around, the arm of the trebuchet around to throw my projectile at the target. And I can change when we release the projectile. What angle should we release the projectile at? So I could just try, right? The easiest way to see if I'm going to hit this or not is to try and look at what happens. So with these parameters, 220 kilogram counterweight, 60-degree release angle, I come up about 15 meters short. So how would I improve this, right? How might I go about improving this my performance here? Well, I could try again, right? And I could try, maybe if my angle is a little bit lower, well, maybe then I'll actually come down and hit my target appropriately, right? And essentially what I'm doing here is I'm using my intuition of the system to say, hey, I think that decreasing my release angle here, taking this release angle and decreasing it, I think that that is going to reduce my error. Or put another way, that the derivative here is going to point me, or the opposite of the derivative is going to point me towards the reducing the error in my system if I decrease the release angle. I could also say increase my counterweight, right? My intuition here would be, well, if I have a heavier counterweight, I'm going to chuck this thing harder, and maybe it'll go farther that way, right? And if I increase my counterweight, well, then maybe we end up going up like this and hitting this, right? And so we can test that, right? And we simply load the trebuchet again, and change my release angle to 55 degrees and launch it again. And sure enough, here we do get better. Right now we're within 7 meters. But now I've tried 2 times, right? And I need to iterate again to get closer to my target. And potentially by that time, my target might have moved, right? They might have gotten on to me that I'm throwing things at them and want to move. And I've expended a lot of resources in testing my system. So there's got to be a better way, and that's where derivatives come in, right? So instead of loading up a medieval siege weapon in my backyard, let's simulate it in Julia, right? We know the equations of motion here. You can imagine this as 3 separate stages of running of equations of motion. You start with the projectile here on the ground, dragging along. Then at some point, the arm lifts the projectile up off the ground and starts hurling it around, whipping it around. And then thirdly, it will release. And at that point, we're at fully ballistic trajectory, right? And within each of these stages, we can fully describe the equations of motion. And there's a really cool website that actually derives all these things for you. You just check out virtualtrebuchet.com, and they've derived the exact equations of motion given the particulars of the parameters of your trebuchet, how long each arm is, how much the counterweight weighs, how much the projectile weighs, so on and so forth. So you could do this, or you could just ask Julia to add the trebuchet package, which implements these equations of motion that goes through, and then it exposes an API where we can ask our trebuchet to shoot or simulate shooting, right? And it's now an integration of equations of motion that we're using here, using a differential equation solver to do the differential equation solution, where we just ask what happens if we have a 5-mile-an-hour wind, release at 55 degrees, and have a 220 kilogram projectile. And sure enough, we get the 94 meters, or a 6-meter miss from our 100-meter target. So that's pretty cool, right? We can take our trebuchet, we can shoot it. But here's where derivatives come into play, right? I can shoot my trebuchet with a given wind speed, a given release angle, and a given weight, a given counterweight, and get the answer, right? Get the distance that it took. I can also ask for the derivative with respect to each one of those parameters. And what that's going to give me back is 3 numbers now, and it's essentially a gradient, a derivative in higher dimensions, where each dimension is pointing in the way that would improve or change my system. So I can see this by increasing my wind. Well, that gives me a big bang for my buck, right? If I increase my wind, I increase my distance significantly. And that makes sense. The wind is blowing in the direction of the target. So increasing the wind gives me a big change. but I can't change that, right? That's a fixed parameter. So it's good to know how big of an effect that has, but it's not something that I can change in hitting my target. The next two numbers, though, are the ones that you want to pay attention to, right? The angle, the release angle, and the weight. So you can see decreasing my release angle, even at 55 degrees, will still increase my distance. And increasing my weight will increase my distance. So this is, the power of the derivative is it tells me exactly how to change the input parameters based upon, a given starting point. And the real magic here is that it's not that much more expensive computationally. If you think about what we're doing, this isn't too obvious at first how impressive this is, right? Where it takes about 2 milliseconds to do one simulation of our shooting. It takes just about half a millisecond longer to do that simulation, but then also give us the derivatives with respect to the wind, with respect to the release angle, and with respect to the counterweight. And if you were to do the naive thing, right, where you just nudged each thing in one direction back and forth, say, you'd actually have to evaluate your system 6 times in order to get these 3 numbers, right? You would nudge your wind a little bit, hold the other 2 things constant, see how much that change in the wind affects your output. You nudge the angle a little bit, see how much that changes your output. And doing each one of those nudges requires 2 full solutions of your differential equation system, which isn't terribly cheap. It's, we're doing this really efficiently and awesomely, but it's still, relatively expensive, 2 milliseconds. And if you want to hear more about, some of the effort that's gone into this, again, Keno's talk from Monday is an awesome place to start, where, he's building atop the architecture that we have today, looking towards our next generation automatic differentiation engine, using all sorts of crazy things like category theory and optical constructions and such. So if you're interested in the exact implementation, check that out. So now we have the gradients. How would we descend to a single target? Well, I could just code up a simple 5-line of code gradient descent thing that just asks for the gradient with respect to my arguments of a given function and updates them using a given learning rate. We can use ADA from literature, very, very standard sort of thing here, where in just a handful of iterations, in fact, in just 10 iterations from our given starting point here with these parameters, we can get within, what is that, 30 centimeters of our target. And it's just looking at, what the derivatives are and how to improve them and as you simulate. And so, before loading up the weapon in my backyard, I can simulate it, do a gradient descent, and figure out how far I need to go, right? And with just 10 evaluations of my function, if I start reasonably close, have a good guess of where I need to start, I can get there pretty quickly. If I am farther away, well, it'll take a little bit longer, but not that much longer. And I can iterate until I'm within a given bound of what I want to hit, right? Where I can keep going until I get close enough for horseshoes or hand grenades or trebuchets. So, what are we doing here? Well, we're taking our simulation, finding the error from a fixed target, computing the derivatives with respect to those inputs, changing them, and repeating, right? And that works, but it's a little slow, and it only works for a given fixed target. So how might I extend this system to do something better, faster, easier? Well, the answer here is that I could build an arbitrary neural network that gives me those control parameters and gives me the weight and the angle I should use for a given arbitrary target. So now what's happening is I take my wind speed, the parameter that I can't change. I take my target location, that other parameter I can't change, pass it through an arbitrary transform here, right? It's a neural network that is potentially deep, potentially complicated. And I, ask it for a given control parameter set, right? I ask for the weights and the angles, and then use those to simulate. I figure out what that error was, and then I use that error to figure out the partial derivatives with respect to all the parameters inside my neural network, right? This is classic machine learning right here, where we are using an error, updating our network. And the cool thing is this network is just taking in our two inputs, giving out our two control signals. And once we've trained this thing, well, we can do this really, really fast, right? We can just have this trained network ask for an aim of, how should we aim our trebuchet given a wind speed of 5 and 100? And it'll give us an approximation of the control parameters, right? A learned approximation of what these control parameters should be. I can then shoot my my simulation, right, and see how close I am. And again, within 40 centimeters of my ideal position here. And if I wanted to improve on this, well, I could go back to that simple gradient descent here, right? Now I have a really, really close starting point that I've trained from lots of examples, and I could train this because I can simulate to my heart's content offline, do this ahead of time, get this network trained up with the parameters that I expect to see in the real world. And once trained, this is blazingly fast, right? It's just doing essentially matrix multiplications. And so it's very, very quick to aim our trebuchet. You can see here it takes on the order of a microsecond now. Instead of 2 milliseconds or multiples thereof, we're now a factor of 1,000 faster and getting the answer. And really, even the training here is fast, where you can see over our entire simulation space of targets ranging from 20 meters to 100 meters, we're able to get down to an error within a meter or two across our entire potential field really quickly, right? And it doesn't take long on my wimpy laptop on a single core to do this in less than a minute. What's even more fun is that games can be played with how you want to make this aiming potentially robust, right? There are multiple solutions. You could have a heavier counterweight and a smaller angle, or vice versa, right? And you can play with these two. Well, you could potentially make your system lean towards being more robust against variations in wind, for example, by simply adding more random noise to the wind when you evaluate your loss function. Just by corrupting that signal, you'll teach the neural network to avoid that and move towards regimes where the wind speed doesn't have as big of an impact on the gradient. So this is really cool, really powerful technique that allows you to use neural networks in conjunction with physical models to quickly gain an understanding of the models. And this is effectively solving that inverse problem, right? I want to go backwards, given my known final output. I want to go backwards from that 100 meter, work my way backwards through the differential equation solver. We can't do that, but what we can do is we can estimate it with a neural network, since neural networks are, arbitrary function approximators. Now, for the third little iteration on ways in which you can play with derivatives within a given physical system, we could learn how to understand a trebuchet model better. Pretend I didn't have that handy virtual trebuchet cheat sheet and someone else had derived the system for me. Pretend I didn't have that. And I might not know some terms of my model, but could describe lots of other terms. So for example, I'm not entirely sure how, the speed of the projectile will interface with the density of air, right? And how that'll interface with the wind speed and such. Maybe that's one aspect that I don't know, but I know all the other equations of motion, right? Well, that one aspect can be represented just kind of as a black box, right? I can block off that aspect of the equation, represented as a black box that's going to be some function, right? Where I want to evaluate some function, given some inputs, And we'll have a single scalar output here in this case, right? You'll want to have some simple input and output relationship. And I could maybe guess at what inputs might be useful here. Maybe it's some of the angles. In this case, this is the equations of motion from the stage 2 of our system here. And I'm blocking out some aspect of this. Well, if I'm in stage 2, probably the angles of the trebuchet arm are going to be important. That's the AQ and the AW. And really, everywhere else they appear, I'm using the sine of these angles. So maybe let's give our function a leg up and think that maybe the sines of these are going to be passed in and potentially mixed with some lengths or some masses. We can have some intuition about which aspect of the system we're simulating and give our arbitrary black box function those inputs. This is feature engineering, right? This is classic feature engineering, where those inputs then end up going into a neural network. We end up with a single output from those inputs. And given a sufficiently complicated neural network, it should be able to learn the aspects of what this should approximate given our local regime. It might not be globally applicable, but I could use, I have some understanding of what data I'm testing it against, and I have some understanding of where that data lives in the entire state space of my system. And so I can then use that to build up this neural network. And of course, it's using the exact same things, right? We're doing the exact same thing. We have our output of our differential equations, and we use that to compare against our ground truth, right? We have real world labeled data, hopefully, that we've tried throwing our trebuchet in the real world, and we want to fit our new models of equations to that. Well, I just, again, find the derivatives with respect to the parameters of my neural network. That neural network happens to be embedded inside my differential equation, but that's just fine. Or the differential equation system will happily call this function as a function. The neural networks in Julia are indeed just functions of their inputs, give you a single output that just have tunable parameters on the outside. So we can train those, get derivatives with respect to them, and iteratively improve our system, again, just using gradient descent or some fancier optimization algorithm. So this is how we can think of taking a derivative 3 ways, right? We started off with the basics of a simple f of x and taking the derivative with respect to that x, and that applies not just to mathy things, but whole simulations and whole scale models where we can nudge the control parameters appropriately. We can take the derivative with respect to an entire approximation network, right? And change the weights of an entire approximation network to give us a quick aiming, a quick approximation of the inverse problem. So that way we can go from our ideal outputs to the control signal. It kind of works backwards for us. Or we could potentially take the derivative with respect to a subset of the model itself, where we have some black box, right, that we're using and doing this. And it doesn't really matter where these tunable parameters live in our system. Julia is happy to do all 3 of these permutations for you, and it just kind of depends upon how you want to learn about your system. So that is the deep dive into how we do this and how you can think about these sorts of problems, how you can think about taking derivatives. And the power of differentiable programming is that we can mix and match these techniques in order to introspect or solve some inverse problem or combinations of both. So with that, I want to dive into the last section of my talk here, where we look at the real world implications of this. And this represents ongoing work by Julia Computing, the MIT lab, many others across pharmaceuticals, engineering, chemistry, manufacturing, climate change, batteries, all sorts of fun projects happening here, where we can look at how differentiable programming is affecting that space and providing new and unique ways in approaching the problems. In general, we've been calling this within the Julia ecosystem scientific machine learning, where we have some model, right? We have some model-based system representation of what we think should happen. It might not be perfect. It might be computationally challenging. It might be very difficult to get its answer. It might be tough to work with, but there is some model, right? And that's often how we approach the world as scientists and even engineers, where we have some intuition. It might not be complete, it might not be accurate, but we have a ground line that we're approaching the problem with. And scientific machine learning allows you to bring that with you and allows you to mix that with large data sets, where if you have labeled data, well, then you're in the perfect position to train some sort of network to tackle your problem. And then it's just a question of where you want to put that network. Is it going to solve the inverse problem? Is it going to introspect some aspect of your system? And the beautiful thing about doing something like like this, where you have a black box and you're digging into your system, the beautiful thing here is that your neural network doesn't need to be as deep or as complex as it would need to be if you were trying to represent the entire system. Right? If I wanted to represent this entire stage or even the entire trebuchet, well, I would need an absurdly large neural network to represent all of the nonlinearities, all of the couplings that's going on here. It would be a huge challenge, in fact, to get a machine learning pipeline to do anything reasonable at all. Whereas if I'm just looking at a small aspect of it, my neural network doesn't need to have the same sort of complexity. It's not representing the same sort of complexity, right? It's just having some small subset of complexity. So that allows us to dig into problems where we have some large-scale complexity and can simultaneously use our model source of information and our data source of information and allow them to work together. And this is driving the case for what are called universal differential equations, this extension of the fact that neural networks can represent arbitrary functions. Well, you combine that with differential equations and you can represent arbitrary models at that point. So I want to talk some about particular systems in which we're finding this to be working quite well and quite compelling. And one is a collaboration that we have with Julia Computing and Puma's AI, where we're working in the pharmaceutical and drug discovery space, specifically quantitative systems pharmacology and physiologically based pharmacokinetics. Those are the mouthful acronyms QSP and PBPK. And the idea here is simple, right? We know how drugs diffuse, or have some understanding of how drugs diffuse through certain compartments of the body, but we don't have the complete understanding. We have some understanding of how drugs are metabolized through the body. We don't have a complete understanding, but we have some understanding. This is a perfect situation for these sorts of neural differential equations, where you can match data to your model, and importantly, if you're able to make these embedded neural networks small enough, you can potentially, after they're trained, go back and introspect these neural networks, see which terms are being used, see which terms are being ignored or zeroed out, potentially drop them out, see if that improves your model, and you can potentially work backwards to the actual model that you want, which is perfect in a space, a regulated space like drug discovery, where regulators aren't terribly pleased about folks using a black box model as part of their drug discovery process, simply because you don't know what's happening. But if you can use a small enough black box that you can introspect it, understand it a little bit better, then you're in good shape to back out a reasonable understanding of the system, and could even drive you towards places of investigation, right? It could narrow down in on particular terms, particular parameters that you might want to adjust and play with in order to stretch the system and see if it's responding in the way that you would expect it to. So in practice, this allows for all sorts of really cool automated discovery of dynamics. We call this deep NLME, and allows you to do all sorts of things, combining your prior scientific knowledge, training those neural networks, and then predicting profiles of potentially new patients, right? And you can then work backwards and potentially discover out mechanistic models from that. A completely other sort of application, still physical modeling based, but totally different, is looking at how buildings, are structures that we live in, how they use energy, how heating systems and cooling systems work with them, and how you're able to represent the cooling systems and figuring out how to make an office building not be freezing in one room and overheating in another, figuring out how to optimize this, because it in the end result, it ends up having a real world cost difference if you can optimize these sorts of things. And this is the same problem, right? We have some rough understanding of the physics of heat dispersion, how the HVAC system's blowing cold air or warm air through the systems. There's some really interesting implications with algebraic equations that aren't necessarily differential, and so these are DAEs, where you can look at how the model interacts with the environment, and in particular with huge nonlinearities, right? And this is a real world case where we have big nonlinearities and discontinuities in our system solution, where if someone opens a door, say, that suddenly changes your system dynamically. And this is the kind of modeling that you need to understand in order to optimize. And so this is something that we're doing, a particular application area. Another place here is training neural networks, and this is an example of that. Just another toy example here of the classic Lotka-Volterra equations, where given just a short time span of our data, we're actually able to model the differential equations, because we knew from the outset that this was going to be a differential equation, right, with some parameters, and doing this sort of thing allowed us to extrapolate out our fit, and importantly allowed us to represent our let's see here, where's my, oh, I lost my cursor. Sorry, the periodic behavior of our system, right? We know that this is a periodic behavior, and even before our neural network saw periodicity, because it was embedded in a differential equation that is geared for periodicity, it figured that out and was able to do this. So this applies both with non-stiff and stiff equations. For those of you who are differential equations experts and understand these much better, the ideas here apply both across huge stiff nonlinear systems and allow you to do this. You can check out some of these papers to see this. Another really cool example is optimization of battery materials, right? Where, again, battery models, we have a rough idea of. We can do this, and we can use neural surrogates for the global sensitivities to automatically refine the equations, automatically figure out what these equations should be based upon data that we've collected in the lab, allow these models to identify material properties and potentially, simulate what materials will be effective to test in the lab. And then you go back to the lab, test another new material, and back and forth. And so this is driving a lot of battery development these days, because testing individual cathodes and anodes, for example, in a battery is going to be wildly, it takes a lot of resources, just like loading my trebuchet did. And so you don't want to test those too many times. I just have one or two more examples here, and then I'll pause for, we can have our discussion towards the end. This is one of my favorite examples, is from a group collaborating out of Caltech and MIT and other institutions, the CLIMA Modeling Alliance, that is trying to simulate the Earth's climate to a degree that a resolution that's never been seen before. Extraordinarily high resolution modeling of, in particular, clouds, which represent big discontinuities and reflectivity and sun absorption, and the ocean surface temperature, which is a huge problem. And in particular, it's one that we have good models for, but they're really expensive, especially if you want to model them on the scale of meters across the entire world, right? That's a huge, huge cost to model, how heat disperses throughout the ocean. And in particular, there tends to be, multiple layers of temperature regimes within the ocean. You need to know where those layers live in order to understand our climate. But goodness, doing this whole 3D simulation of the entire Pacific Ocean, plus the Atlantic Ocean, and 2/3 of the Earth's surface area, is far too expensive and just simply intractable to do. And so you can do the same sort of thing we did with our trebuchet, where you approximate the simulation with a neural network under parameters that you have identified and you have fully understand. And then you can introspect that neural network, make sure that it matches the performance that you need. And you can see, indeed, in these bottom graphs, the dashed line is our neural network representation of the full 3D compute heavy simulation. And the solid lines are the, I'm sorry, I have that backwards. The solid lines are the simulations, and the dashed lines are the neural networks. And we're matching those pretty darn close. And in this case, it's close enough to drive the rest of our models forward, and allows us to bring this a huge acceleration speed up, right? A 15,000-fold acceleration speed up over the 3D simulation. And it's done automatically identified through neural networks based on data that we've observed, or rather based on data that we've already simulated. And we can simulate the data that we need to do this, but we only need to simulate a subset of the world, right? We don't need to do the whole thing. We can let the neural network grab on to the rest of it. So I think with that, we're running out of time. There's lots of other application areas ranging from, machine learning and training reinforcement learning. AlphaZero is an awesome package in Julia, as well as an extension of the Celeste project, where we did image recognition and Bayesian inference across the night sky. A huge petascale Julia project, and Turing.jl extends that and makes that available more broadly to you. And it's an awesome resource for modeling, and is built atop this differential programming model. So with that, I want to thank you so much for your attention, and I'm really excited for this discussion. I hope we can have, I know it's a Friday afternoon, but I hope there's some good questions, and we can have a chat about how differentiable programming is poised to move a lot of sciences forward across lots of domains.
Thank you, Matt. Here's Russ. I do have a few questions that I could use to start, but I'd rather if other audience started with questions. While people collect their thoughts, I want to thank you for this fantastic talk and a great introduction to the many applications. And I'm monitoring also Clouder.
Oh, great.
There is no question right there. There is a nice reminder that we can meet the speakers in the breakout room at 2:20, I think. Can I encourage questions from the Zoom audience or Clouder audience? Okay, well, let me ask one question that I would like to start with. So you gave many examples of what the models could be, how they can capture the domain knowledge or the intuition of the modeler, right? And how you can build an entire model or just a partial model to plug into the system. You didn't talk as much about what are the various algorithms that you use then to fit the model. Are all of them gradient descent, or do you use differentiable programming to derive what you could say constraints which you then feed into a solver other than gradient descent? Perhaps one that tries to maintain some hard constraints which could be useful in engineering applications.
Yeah, absolutely. So there's a whole nother subset of Julia that I didn't even touch on. The jump ecosystem within Julia is geared for those kinds of constrained optimization problems where you can, build out your let's see here. Yeah, these sorts of mathematical optimization problems, like, for example, Sudoku, right, where you have a constrained problem set that is not as well geared for gradient descent, right? It's more of a constraint solution problem. Right. And Jump and Optim are kind of the programming toolkits that build atop of those, and they started out by connecting into traditional solvers, right? The traditional commercial constraint-based solvers like Gurobi and things like that. In doing so, they've built up this entire domain-specific language that's solver agnostic, that allows you to swap out those solvers. And so there's new research going on here with respect to differentiable programming. And I unfortunately am not fully on top of that, but I do know that there is work going on there that is digging into how you can express these sorts of constraint programming and integer programming examples that aren't as well served with gradient descent.
I see. I was thank you for that pointer. I didn't know about that part of Julia, but I was actually interested in using a derivative of your model in constraint solvers that go beyond gradient descent, perhaps that optimize several losses, but not under a combined metric, but one that perhaps some of them are hard constraints that you want to maintain for sure. And perhaps you can think of it as an outer loop over a gradient descent optimization or some other such thing. And from the little I know about the numerical constraint solving, that these solvers do appreciate having access to derivative of the model to do their solving. So I was wondering whether you occasionally use such solvers, or all of these fantastic applications actually are driven by gradient descent, meaning a single loss optimization.
Yeah, so actually in the differential equations solvers themselves, they rely upon the derivatives of the problem that they're solving in order to estimate and simulate and step forward, right? And there's support within the differential equations ecosystem for these algebraic equations, that is hard constraints that aren't derivative based, but are these algebraic equations that are hard constraints like that you cannot violate. And there's a special way of expressing that to the differential equations solvers. And there's a bunch of solvers within the differential equations ecosystem that can support DAEs, as they're called, that then you can take that and run with. So I think that would be more along the lines of your initial question. I may have not understood.
I think probably well, I wasn't sure what I was asking. I was wondering perhaps of just other applications of differentiating besides gradient descent.
Yeah. So the differential equations, in fact, themselves lean on derivatives, and it's caused a bit of a problem because then suddenly you start needing second order and third, you need to ask the compiler for potentially second order and third order derivatives. And that's really where, Kano's work on the compiler side of things is helping us drive things forward, where we're able to support higher level derivatives, where right now actually this timing betrays some significant compile time. This is the second time that you've run it, you get 2.5 milliseconds, but the first time you run it, it does take some compile time to compile all the machinery, both to take the gradients and the function itself, right? You're compiling this, and this works well with Julia's just-in-time nature of the system.
Mm-hmm. Mm-hmm. Thank you, Matt. I'd like others to ask questions.
Yeah, I have a question, Matt, if I can go next. So lovely talk. I especially enjoyed all these cool scientific applications. One thing that came to mind is that if you had to go do differential equation kind of work, what are the things that Julia language kind of uniquely enables, or maybe enables in a uniquely convenient way compared to using anyone else's system that does automatic differentiation in some form? So could you say something about that?
Sure. Well, I mean, I think the biggest advantage that we have is that nearly all of our packages are written in Julia itself, which gives the compiler a whole lot more leverage on understanding what's going on. It has access to all sorts of reflection tools, all sorts of crazy compiler tricks can happen without the user needing to tell the system how that works. And so, for example, as compared to other systems where you need to explicitly, almost in a meta-programming way, describe to the program your graph of computation in order for it to take the derivative of it. In Julia, it's as simple as writing the functions themselves and asking the compiler for the derivative. Now, that's not entirely fair of all other systems, right? There are systems that do this a little bit better, but there are cases where you really need to describe to the compiler, as a user, you need to say, hey, this is my neural network kind of at a meta level, and this is where the control flow goes and things like that, and it can be challenging to do that. So that's one mechanism in which I think we're doing well. The other is just simply how extensible this is, where the differentiable framework that we have is built upon what we call chain rules. It's a package that describes those sorts of derivatives that you memorized in calculus. They describe the fact that, hey, instead of looking inside the sine function, for example, don't bother looking inside of the sine function to see what multiplications and additions are being used to approximate it. Instead, just swap it out with a cosine function, because we know these from first principles. And so there's a fully extensible ecosystem of these rules that are used in all of our automatic differentiation toolkits. And I think one of the surprising things here is that there's not, at least not yet, a golden egg, a perfect solution for doing automatic differentiation. There's forward mode, there's reverse mode, there's all sorts of different ways of approaching this, and depending on your task, there are going to be different advantages in computational complexity or usability or functionality that are going to give you a leg up. And in Julia, it's extraordinarily simple to swap them out, and they all live on the same abstract frame that we're slowly teaching Julia how to do calculus through this awesome open source community, extensively teaching it how to do this. So I guess those are two examples of where I see Julia as having a huge leg up, but I'm sure others have other viewpoints on this as well.
Considering that we still have some time, I'd like to ask one more question. In the early three examples, you show how, essentially propagating gradients was a very versatile technique. I'm wondering whether you could also use it to identify weaknesses in the hard-coded model, the one that provides the intuition, right? Imagine that there are mistakes in it due to misconceptions or such about the modeled phenomena. Can you point to the sources of error in the model by perhaps discovering where relaxing those hard-coded parts of the model would be most beneficial?
Sure, or even just simply adding an error term, right? Like that error term that we're so used to adding in just kind of as a abstract representation, right? You can model that error in terms of a neural network, and throw a bunch of inputs at it, and take some guesses as to what that error term might be a function of. Throw some data at it, iterate over it, and see where that goes. See if you're able to train that neural network to represent the error. It could be that it's not trainable either because it is fully uncorrelated with any of the things that you're guessing to be inputs, or is a challenging aspect of it. But it could also lead to that kind of new intuition, and give you potential avenues for ways of fleshing out your model even more. Yeah.
I see. So you could do the error term on the entire model, and of course you could do it on individual components to find out perhaps which of them need more compensation.
Right.
Perhaps find out which of them are not correct models, if you want to understand which of them are actually not modeling the reality well. Okay, that's very interesting. That's very interesting. Are there other questions? Trying to understand if the next talk is starting in 3 minutes and what we need to actually do here. Perhaps we'll need to wait for Satish to tell us. Can you tell us?
For this QA rebase session, the time allocated for question and answer is up to 40 minutes. We don't have to use all of 40 minutes, but it's up to 40 minutes. I think the announcements you might be seeing in Clouder could be with respect to other sessions happening concurrently.
Okay, that's what I was confused about. I see. Wonderful. I see. I'd like to ask a question that perhaps is for Kino about compilation. Right? You mentioned the overhead of having to compute the derivative again, and it of course gets faster with once the sort of model of the forward computation is built. But I'm also curious whether you do some sort of staging of the computation in the sense that you actually don't have to recompute the derivative as the point moves, because symbolically the computation is the same. You just need to plug in different sort of primal values. Is that something you do?
That is an aspect of the system that I'm not, that is a Kano question, to be sure. I'm not as certain on that. I think the naive thing, the default thing, is very pessimistic, right? Where it's effectively the halting problem, trying to figure out what range of values the control flow that you happen to go through is effective for, right?
Yes.
And so I don't think it's not something I've tried to do, and it's not something that I've heard of Kino trying to do. But my gut reaction there is that it's roughly equivalent to solving the halting problem, is trying to extend that range, right? You're trying to see if you're trying to see if the branches are the same, and the control flow is the same, given perturbations in your arguments, I guess.
That makes sense. Thank you.
Yeah.
Well, if we don't have more questions, I am apparently suggested to close the session. And if I understand from the chat in Clouder, we should move to the Meet the Speaker MTS room. And I don't know how we'll do it, but I suppose we'll figure out in Clouder once we poke around. So I want to thank you, Matt, again,
Sounds
and
great.
I hope to
Thank you
chat
so
with you
much.
in a minute or so in a separate channel. I have a few more questions that are a little bit off this particular topic, but perhaps suitable for that forum.
Sure.
Thank you.
All right. Take care, everyone. Thank you so much.